The number 9.94 represents the voltage drop in volts per 1000 feet of conductor. To determine if this voltage drop is acceptable, you need to compare it to the allowable voltage drop for the circuit. The allowable voltage drop is typically determined by the equipment being powered and the application. For most residential and commercial applications, a voltage drop of 5% or less is considered acceptable. In this case, the voltage drop per 1000 feet is 9.94 volts. For a total distance of 1600 feet, the total voltage drop would be calculated as follows. Voltage drop equals 9.94 volts per 1000 feet multiplied by 1600 feet, which equals 15.9 volts. This voltage drop is higher than the allowable 5% for a 120 volt circuit. Therefore, using 8 American wire gauge wire for this application would result in an unacceptable voltage drop. You would need to use a larger wire size, such as 6 American wire gauge or 4 American wire gauge, to reduce the voltage drop to an acceptable level. Let's delve deeper into understanding voltage drop, its calculation, and acceptable limits in electrical circuits. Voltage drop is the decrease in voltage along a conductor through which current is flowing. It's an inevitable phenomenon due to the resistance of the wire. Excessive voltage drop can lead to various problems, including dimming lights, malfunctioning equipment, and even overheating of conductors, potentially causing fires. Therefore, it's crucial to calculate and manage voltage drop to ensure safe and efficient operation of electrical systems. The formula for calculating voltage drop is voltage drop equals current multiplied by resistance. However, in practical applications, we often use a more detailed formula that considers the wire's length and the specific resistance per unit length. This formula is voltage drop equals 2 multiplied by K multiplied by I multiplied by D divided by the circular Mills area, where K is the direct current resistance factor for the conductor material expressed in ohms circular mil per foot, I is the current in amps, D is the one-way distance in feet, and Cm is the circular Mills area of the conductor. The factor of 2 accounts for the fact that the current travels both to and from the load. The K factor depends on the conductor material. For copper, it's approximately 12.9 ohms circular mil per foot, and for aluminum, it's approximately 17 ohms circular mil per foot. These values are typically used for calculations at a specific temperature, often 75 degrees Celsius. Now let's discuss acceptable voltage drop limits. The National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders. A commonly accepted guideline is a maximum voltage drop of 3% in branch circuits and 5% in feeders, resulting in a total maximum voltage drop of 5% to the farthest point of utilization. However, it's essential to consider the specific requirements of the equipment being powered. Some sensitive electronic devices may require even tighter voltage regulation. To determine the appropriate wire size for a given application, you need to consider several factors, including the load current, the distance, the allowable voltage drop, and the conductor material. Firstly, determine the load current. Calculate the current required by the load using the formula current equals power divided by voltage. Ensure you're using the correct voltage for the circuit, such as 120 volts or 240 volts for single-phase systems, or 208 volts or 480 volts for three-phase systems. Secondly, determine the distance. Measure or estimate the one-way distance from the source to the load. For long runs, accurate distance measurements are crucial. Thirdly, determine the allowable voltage drop. Determine the maximum acceptable voltage drop based on the NEC guidelines and the equipment requirements. Express this as a percentage of the source voltage. For example, for a 120 volt circuit with a 3% allowable voltage drop, the maximum voltage drop would be 3.6 volts. Fourthly, calculate the minimum circular Mills area. We arranged the voltage drop formula to solve for the circular Mills area. The formula becomes circular Mills area equals 2 multiplied by K multiplied by I multiplied by D divided by the allowable voltage drop. Fifthly, select the appropriate wire size. Use a wire size chart to find the wire size with the circular Mills area equal to or greater than the calculated value. Standard wire sizes are expressed in American wire gauge or AWG. Smaller AWG numbers indicate larger wire sizes. Common wire sizes include 14 AWG, 12 AWG, 10 AWG, 8 AWG, 6 AWG, 4 AWG, and so on. Sixthly, verify the ampacity. Ensure that the selected wire size has an ampacity rating sufficient to carry the load current. Ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. The NEC provides ampacity tables that list the ampacity ratings for different wire sizes and insulation types. When selecting a wire size, it's always best to err on the side of caution and choose a larger wire size if there's any doubt about the ampacity or voltage drop. Using a larger wire size will reduce the voltage drop and improve the overall performance and safety of the electrical system. In addition to calculating voltage drop, it's also important to consider other factors that can affect the performance of electrical circuits, such as temperature, conduit fill, and dirting factors. High temperatures can increase the resistance of conductors, leading to increased voltage drop. Conduit fill refers to the percentage of the conduit's cross-sectional area occupied by conductors. Excessive conduit fill can reduce the heat dissipation of the conductors, leading to high temperatures and dirting. Dirting factors are used to reduce the ampacity of conductors when they are installed in certain conditions, such as in close proximity to other conductors or in high-temperature environments. The NEC provides tables and guidelines for dirting conductors based on these factors. Let's look at some practical examples of voltage drop calculations. Example 1: a 120-volt circuit supplies a 10-amp load located 100 feet away. What is the minimum size copper wire required to keep the voltage drop within 3%? Firstly, calculate the allowable voltage drop. 3% of 120 volts is 3.6 volts. Secondly, calculate the required circular Mills area. Using the formula circular Mills area equals 2 multiplied by K multiplied by I multiplied by D divided by the allowable voltage drop, we get circular Mills area equals 2 multiplied by 12.9 multiplied by 10 multiplied by 100 divided by 3.6, which equals 7,167 circular Mills. Thirdly, select the appropriate wire size. From a wire size chart, we find that 12 American wire gauge wire has a circular Mills area of 6,530 circular Mills, which is not sufficient. 10 American wire gauge wire has a circular Mills area of 10,380 circular Mills, which is sufficient. Therefore, the minimum size copper wire required is 10 American wire gauge. Fourthly, verify the ampacity. According to the NEC, 10 American wire gauge copper wire with type TW insulation has an ampacity of 30 amps, which is sufficient for a 10 amp load. Example 2: a 240-volt circuit supplies a 20 amp load located 200 feet away. What is the minimum size aluminum wire required to keep the voltage drop within 5%? Firstly, calculate the allowable voltage drop. 5% of 240 volts is 12 volts. Secondly, calculate the required circular Mills area. Using the formula circular Mills area equals 2 multiplied by K multiplied by I multiplied by D divided by the allowable voltage drop, we get circular Mills area equals 2 multiplied by 17 multiplied by 20 multiplied by 200 divided by 12, which equals 11,333 circular Mills. Thirdly, select the appropriate wire size. From a wire size chart, we find that 8 American wire gauge aluminum wire has a circular Mills area of 6,530 circular Mills, which is not sufficient. 6 American wire gauge aluminum wire has a circular Mills area of 16,620 circular Mills, which is sufficient. Therefore, the minimum size aluminum wire required is 6 American wire gauge. Fourthly, verify the ampacity. According to the NEC, 6 American wire gauge aluminum wire with type TW insulation has an ampacity of 40 amps, which is sufficient for a 20 amp load. In summary, calculating and managing voltage drop is essential for ensuring safe and efficient operation of electrical systems. By understanding the factors that affect voltage drop, using the appropriate formulas, and following the NEC guidelines, you can select the correct wire size and minimize voltage drop to acceptable levels. Remember to always consider the specific requirements of the equipment being powered and consult with a qualified electrician if you have any doubts or questions. By paying attention to voltage drop, you can prevent problems such as dimming lights, malfunctioning equipment, and overheating of conductors, and ensure the long-term reliability and safety of your electrical systems. Now let's focus on some advanced considerations related to voltage drop in more complex electrical systems. Firstly, voltage drop in three-phase systems. The voltage drop calculation for three-phase systems is slightly different than for single-phase systems. In a balanced three-phase system, the voltage drop is calculated using the line-to-line voltage and a factor of the square root of 3, which is approximately 1.732. The formula for voltage drop in a three-phase system is voltage drop equals the square root of 3 multiplied by K multiplied by D divided by the circular Mills area. Secondly, voltage drop in multi-wire branch circuits. Multi-wire branch circuits, or MWBCs, are circuits that share a neutral conductor. In an MWBC, the voltage drop on the neutral conductor can be significant if the loads on each leg of the circuit are not balanced. To minimize voltage drop in MWBCs, it's important to balance the loads as much as possible and to use a neutral conductor that is sized appropriately for the unbalanced load. Thirdly, voltage drop in long feeders. For long feeders, the voltage drop can be significant, especially if the load current is high. In these cases, it may be necessary to use multiple conductors in parallel to reduce the voltage drop. When using conductors in parallel, it's important to ensure that all conductors are of the same size, material, and length, and that they are properly terminated to ensure equal current sharing. Fourthly, voltage drop in systems with nonlinear loads. Nonlinear loads, such as electronic devices with switching power supplies, can generate harmonic currents that can increase the voltage drop in electrical systems. Harmonic currents can also cause overheating of transformers and other equipment. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to oversize the neutral conductor. Fifthly, using voltage drop calculators. There are many online voltage drop calculators available that can simplify the process of calculating voltage drop. These calculators typically require you to input the load current, distance, voltage, conductor material, and wire size, and they will calculate the voltage drop and provide recommendations for the appropriate wire size. Sixthly, using specialized software. For complex electrical systems, specialized software can be used to model the system and calculate voltage drop under various load conditions. These software programs can take into account factors such as conductor temperature, conduit fill, and dirting factors to provide more accurate results. Seventhly, the importance of proper installation. Proper installation practices are essential for minimizing voltage drop and ensuring the safety and reliability of electrical systems. Conductors should be properly terminated and tightened to minimize resistance at connections. Conduit should be properly sized and installed to ensure adequate heat dissipation. And conductors should be protected from physical damage to prevent shorts and ground faults. Eighthly, regular maintenance and inspection. Regular maintenance and inspection of electrical systems can help to identify and correct problems that can lead to increased voltage drop. Connections should be inspected for looseness or corrosion, and conductors should be checked for damage. Additionally, load measurements should be taken to ensure that the loads are balanced and that the system is operating within its design parameters. Ninthly, energy efficiency considerations. Minimizing voltage drop can also improve the energy efficiency of electrical systems. By reducing the voltage drop, you can reduce the amount of energy that is lost in the conductors, which can save money on your electricity bill. Tenthly, consulting with a qualified electrician. If you are not comfortable working with electrical systems, or if you have any doubts about the safety or performance of your electrical system, it's always best to consult with a qualified electrician. A qualified electrician can assess your electrical system, identify any potential problems, and provide recommendations for how to correct them. By following these advanced considerations, you can ensure that your electrical systems are operating safely, efficiently, and reliably. Remember to always prioritize safety when working with electricity, and to consult with a qualified electrician if you have any doubts or questions.